Methods for achieving population inversion. There are 5 major methods by which the pumping can be achieved. They are optical pumping, direct electron excitation, inelastic atom-atom collisions, direct conversion, and chemi-excitation. Optical pumping. Optical pumping is the process of exciting an atom from the lower energy level to the higher energy level by a photon of energy h nu. This figure depicts the optical pumping process. This technique was developed by Alfred Asteller, French physicist, who is one of the Nobel laureates in 1966. The pump power should be higher than the lasing threshold. The lasing threshold is the lowest excitation level at which the output is dominated by stimulated emission rather than spontaneous emission. Electrical discharge method or direct electron excitation. The electrical discharge method is a basic principle behind all the gaseous lasers. In this process, electrons produced in an electrical discharge tube are accelerated to higher velocities by a strong electric field. These accelerated electrons collide with the gas atoms or molecules. During this process, energy is transferred from the electrons to the gas atoms or molecules. Hence, a large amount of atoms got excited, resulting in population inversion. This process of excitation is called electrical discharge method. The energy transfer is represented by the equation A plus E star, which gives A star plus E prime. A is the gas atom at the ground state. E star is the accelerated electrons with kinetic energy. A star is the same gas atom in the excited state, whereas E prime is the same electron with lesser energy level. Electrical pumping is used in almost all the gaseous lasers, as optical pumping is not efficient for gas lasers. Inelastic atom-atom collision. In some gaseous lasers, a mixture of gases is used. In these lasers, due to the electron bombardment, one part of gaseous atom gets excited with higher energy level. The excited gaseous atom makes collision with another gaseous atom and bring it into an excited state. This process of excitation is known as inelastic atom-atom collision, and this figure is depicted the schematic representation of inelastic atom-atom collision. Consider there is a mixture of two gaseous atoms, say A and B. A gaseous atom A can be raised to an excited state by the collision of electron. This inelastic atom-atom interaction can be written mathematically as A plus E, which gives A star plus E1. The excited atom A star makes collision with another gaseous atom B and brings the atom B to the excited state. Hence, atom A loses energy and returns to lower state, that is A star plus B, which gives A plus B star. The inelastic atom-atom collision is used in helium neon and carbon dioxide lasers. Direct conversion. In this method, direct conversion takes place in a semiconductor medium like gallium arsenide. When electrical charge is applied to gallium arsenide semiconductor, electrons and holes are recombined with each other, releasing a light energy of energy h nu. Here, an electrical energy is directly converted into light energy. This method is called direct conversion. This direct conversion method is employed in semiconductor lasers. Chemi-excitation. Chemical pumping in lasers involve the use of a chemical reaction to provide the energy needed to excite the lasing medium. In this process, the chemical compound involved in releasing the energy is in a form of heat or light when ignited or stimulated. This energy then excites the atoms or molecules in the lasing medium, causing them to emit coherent light. One common example is the use of a mixture of gases like a mixture of carbon dioxide, nitrogen and helium in a carbon dioxide laser. This method relies on the conversion of chemical energy into electromagnetic radiation, offering distinct advantages and applications across various fields. Unlike other pumping methods such as optical or electrical pumping, which rely on external energy sources like lamps or electrical currents, chemical pumping offers self sufficiency in energy provision. This self-contained nature makes chemical lasers particularly suitable for applications where continuous or high-power operation is required, such as military applications, industrial cutting, and scientific research. One of the most prominent examples of chemical pumping is found in carbon dioxide laser.